All right, we are back, and I am working on 753, 522. I decided to eat dinner and just knock that out since I was off anyways. So we'll go all the way to 782, and then I'll call it a night. Okay. So this is about process resources. Pretty light reading on this one. Not super intense. Not super complicated. Just a bunch of different resources, like the R limit stuff. So it'd be nice to get kind of an overview of what all the different resource limits and stuff are, even if it's super high level. Okay, let's get started here. Each process consumes system resources such as memory and CPU time. This chapter looks at resource-related system calls. We begin with the getRUsage system call, which allows a process to monitor the resources that it has used or that its children have used. We then look at setRLimit and getRLimit. So it's getRUsage, setRLimit, getRLimit system calls, which can be used to change and retrieve limits on the calling process consumption of various resources. Process resource usage. The getRUsage system call retrieves statistics about various system resources and used by the calling process or by all of its children. So you can pass in a who argument, and it writes into the RUsage struct. The who argument specifies the processes for which resource usage information is to be retrieved. It has one of the following values: RUsage self, return information about the calling process; RUsage children, return information about all the children of the calling process that have terminated and been waited for. So you don't get resource usage about children that are non-terminated or haven't been waited for. RUsage thread, return information about the calling thread. This is Linux specific. The RES usage argument is a pointer to a structure of type RUsage, defined as shown in listing 36.1. So you got obvious CPU time, user system CPU time, maximum size of the resident set RSS, the integral shared text memory size, the integral unshared data memory used, integral unshared stack memory used. So those are all memory related. Soft page faults, IO not required. Hard page faults, IO required. Swaps out of physical memory. Block input operations via file system. Block output operations via file system. IPC message sent, IPC message received, signals received. Voluntary context switches, process relinquished CPU before its time slice expired. Involuntary context switches, higher priority process became runnable or time slice ran out. As indicated in the comments in listing 36.1 on Linux, many of the fields in the RUsage structure are not filled in by getRUsage or wait 3 and wait 4. Or they are filled in only by more recent kernel versions. Some of the fields that are unused on Linux are used on other Unix implementations. These fields are provided on Linux so that if they are implemented at a future date, the RUsage structure does not need to undergo a change that would break existing application binaries. Although getRUsage appears on most Unix implementations, it is only weakly specified in Subspeed 3, which specifies only the fields RU time and RS time. In part, this is because the meaning of much of the information in the RUsage structure is implementation dependent. The RU time and RUS time fields are structures of the time val, of type time val, which return the number of seconds and microseconds of CPU time consumed by the process in user mode and kernel mode, respectively. Similar information is retrieved by the times system call described in section 10.7. Link specific proc pid stat file exposes some resource usage information, CPU time, and page faults about all processes on the system. See proc 5 manual page for the details. The R usage structure returned by the get R usage children operation includes the resource usage statistics of all the descendants of all of the calling process. For example, if we have 3 processes related as parent, child, and grandchild, then when the child does wait on the grandchild, the resource usage values of the grandchild are added to the child's R usage children values. When the parent performs a wait on the child, the R usage values of both the child and the grandchild are added to the parent's R usage children values. Conversely, if the child does not wait on the grandchild, then the grandchild's resource usage are not recorded, and the R usage children values of the parent. It's kind of like this data is attached to the exit code of the process, like similar to how the kernel holds on in like its process table holds on to the exit code. It's also holding on to this R usage structure, and it's reporting it via wait. And if you don't wait, you don't get the value reported. Conversely, if the child does not wait on the grandchild, then the grandchild's resources are not recorded. For the R usage children operation, the RU max RSS field returns a maximum resident set size among all the descendants of the calling process rather than a sum for all descendants. I wonder what the utility of this bag of metrics is when you introduce something like BPF. Because all these statistics, like BPF can just monitor this stuff, like whatever arbitrary kernel thing that you want. You can monitor whatever you want in real time. It doesn't have to propagate statistics through this waiting and stuff. You can just like store the data and hash inside or what they call it, a map inside the kernel and report it asynchronously to user space. Substitute specified sick child is being ignored so that children are not turned into zombies that can be waited on. Then the child statistics should not be added to the values returned by our usage children. However, as noted in section 2633 in kernels before 269, Linux deviates from this requirement. If sick child is ignored, then the resource usage values for dead children are included in the values returned for our usage children. That's the other thing. It's like, it's only after you waited can you collect this information, and it's like unreliable for children. Like for the current process, it could be reliable because you can just access it whenever you want. Process resource limits. Each process has a set of resource limits that can be used to restrict the amounts of various system resources that the process may consume. For example, we may want to set resource limits on a process before exiting an arbitrary program, or executing, I should say, an arbitrary program. If we are concerned that it may consume excessive resources, we can set the resource limits of the shell using the ulimit built-in command, limit in the C shell. These limits are inherited by the process that the shell creates to execute user commands. Since kernel 2624, the Linux specific proc pid limits file can be used to view all of resource limits of any process. Okay, let's cat that out. Cat proc self limits. Max CPU time, file size, data size, stack size, core file size, resident set, processes, open files, locked memory, address space, file locks, pending signals, message queue size, nice priority, real-time timeout. The file is owned by the real user ID of the corresponding process, and its permissions allow reading only by that user ID, or by a privileged process. The get R limit and set R limit system calls allow a process to fetch and modify its resource limits. So you got get R limit, and then you pass in the resource as an integer, and then it writes it to the R limit struct. This is R usage and R limit. And then there's a set R limit, which is where you pass it in to be set. And it's not mutated because it's a const. The resource argument identifies the resource limit to be retrieved or changed. The R limit argument is used to return resource limit values or to specify new resource limit values, and is a pointer to a structure containing two fields, the R limit cur and R limit max, which is cur is a soft limit, and then hard limit is ceiling for R limit cur. Okay. Yeah, I don't quite understand soft and hard limits, so hopefully they describe those. These fields correspond to two associated limits for a resource, the soft and hard limits. The soft limit governs the amount of resource that may be consumed by the process. A process can adjust the soft limit to any value from 0 up to the hard limit. Okay, so what we're saying is like you as a process, your current value is going to be this, which would be a limit, but it's your current limit, and you can increase it up to max. That makes sense. For most resources, the sole purpose of the hard limit is to provide a ceiling for the soft limit. A privileged process can adjust the hard limit in either direction, as long as the value remains greater than the soft limit. But an unprivileged process can adjust the hard limit only to a lower value irreversibly. The value R limit infinity and the R limit cur or R limit max means infinity, no limit on the resource, both when retrieved via get R limit and when set via set R limit. So it's just a constant declared somewhere. In most cases, resource limits are enforced for both privileged and unprivileged processes. One thing I just realized is that like all of these like standards, they're all in C. Like I mean, it seems kind of obvious, but like the realization is that like, okay, if you want to compete against C, like it has like decades of just being the standards for all of this stuff. Like there's no competing against that. You're not gonna replace all these, like even this book just has all these constants defined and everything, structures and everything, and like it's the C code itself, the C APIs that are standardized. It's not actually the representations underneath. So you can write your own language that has its own it's the same representations, but it's not the same API, you know. I mean, you can simulate the same API and kind of make it to where symbols are the same and stuff like that, so it's familiar to people who are familiar with the C API, but yeah, I mean, C just has like a massive like head start on and is embedded into all these standards. Okay, in most cases, resource limits are enforced for both privileged and unprivileged processes. They are inherited by child processes created via fork and are preserved across exec. The values that can be specified for a resource argument of getRLimit and setRLimit are summarized in table 36.1 and detailed in section 36.3. Although a resource limit is a per process attribute, in In some cases, the limit is measured against not just the process consumption of the corresponding resource, but also against the sum of resources consumed by all processes within the same real user ID. The R limit and proc limit, which places a limit on the number of processes that can be created, is a good example of rationale for this approach. Applying this limit against only the number of children that a process itself created would be ineffective, since each child that the process created would also be able to create further children, which could then create more children, so on and so forth. Instead, the limit is measured against the count of all processes that have the same real user ID. Note, however, that this resource limit is checked only in the processes where it has been set, i.e. the process itself and its descendants, which inherit the limit. If another process owned by the same real user ID has not set the limit, or has set a different limit, then that process capacity to create children will be checked according to the limit that it has set. Well, that's confusing. As we describe each resource limit below, we note those limits that are measured against the resources consumed by all processes with the same real user ID. If not otherwise specified, then a resource limit is measured only against the process's own consumption of the resource. Be aware that in many cases, the shell commands for getting and setting the resource limits, ulimits in bash and corn shell, and limit in C shell, use different units from those used in get R limit and set R limit. For example, the shell commands typically express the limits on the size of various memory segments in kilobytes. Resource values for get R limit and set R limit. Process virtual memory size. Core file size, CPU time, process data segment, file size, locked memory, message queue, nice setting, nice value. Number of file descriptors, number of process for the real user ID, resident set size, real-time scheduled priority, real-time CPU time, sig pending stack. Before going to specifics of each resource limit, we look at a simple example of the use of resource limits. Listing 36.2 defines the function print R limit, which displays a message along with the soft and hard limits for a specific resource. The R limit data type is typically presented with the same way as represented in the same way as offset T to handle the representation of R limit F size, the file size resource limit. For this reason, when printing R limit T values as set in listing 36.2, we cast them to long and use the long printf specifier as explained in section 510. The program in listing 36.3 calls set R limit to set the soft and hard limits on the number of processes that a user may create. Uses the print R limit function listing 36.2 to display the limits before and after the change, and then creates as many processes as possible. When we run the program, setting the soft limit to 30 and the hard limit to 100, we see the following. So it's initial maximum process limits, then it sets its soft and hard, then it creates a bunch of children, and then once it gets to 4, it dies? What? That doesn't make sense. That's just truncated. Oh, probably because there's like other parents with the same. I don't know. In this example, the program managed to create only 4 new processes because 26 processes were already running for this user. Yeah, it's what I gathered. Boop. Let's skip past the code here. I don't think it's important. Unrepresentable limit values. In some programming environments, the R limit data type may not be able to represent the full range of values that could be maintained for a particular resource limit. This may be the case on systems that offer multiple programming environments in which the size of the R limit T data type differs. Such systems can arise in large file compilation environments with a 64-bit off-T is added to a system on which off-T was traditionally 32 bits. In each environment, R limit would be the same size as off-T. This leads to a situation where a program with a small R limit T can, after being exec'd by a program with a 64-bit off-T, inherit a resource limit, e.g. a file size limit that is greater than the maximum R limit T value. To assist portable applications in handling the possibility that a resource limit may be unrepresentable, Substitute 3 specifies two constants to indicate unrepresentable limit values. R limit saved cur and R limit saved max. If the soft resource limit can't be represented in R limit T, then get R limit or return R limit saved cur in R limit cur field. Okay. If all possible resource limit values can be represented in R limit T, then Substitute 3 permits an implementation to define R limit save cur and R limit save max to be the same as R limit affinity. This is how these constants are defined on Linux, implying that all possible resource limit values can be represented in R limit T. However, this is not the case on 32-bit architectures such as x86 32. On those architectures, in a in a large file compilation environment, glibc definition of R limit is 64-bit wide, but the kernel data type for representing a resource limit is unsigned long, which is only 32 bits wide. Current versions of glibc deal with the situation as follows. If a program compiled with file offset bits is equal to 64 tries to set a resource limit to a value larger than can be represented in a 32-bit unsigned long, then glibc wrapper for the set R limit silently converts the value to R limit infinity. In other words, the requested setting of the resource limit is not honored. Because utilities that handle files are normally compiled with file offset bits 64. I'm going to skip this comment because this is like horribly outdated. I tried testing this stuff on my local machine, and basically glibc doesn't do any of this stuff anymore. Details of specific resource limits. In this section, we provide details on each of the resource limits available in Linux, noting those that are Linux specific. R limit as. Okay, these are all this big dictionary of limits. And then that's it for the chapter. So let's get through these. So R limit AS. I have no idea what that would mean off the top of my head. So the R limit AS limit specifies the maximum size of the process's virtual memory address space. Okay, AS is address space. In bytes. Attempts to break, mmap, all that stuff to exceed this limit fail with error enomem. In practice, the most common place where a program may hit this limit is in calls to functions in the malloc package, which make use of break and memmap. Upon encountering this limit, stack growth can also fail, with the consequences listed below for R limit stack. R limit core. The R limit core limit specifies the maximum size in bytes for core dump files produced when the process is terminated by certain signals. Production of a core dump file will stop at this limit. Specifying a limit of 0 prevents creation of core dump files, which is sometimes useful because core dump files can be very large and end users usually don't know what to do with them. Another reason for disabling core dumps is security, to prevent the contents of program's memory from being dumped to disk. If the R limit size, F size limit, is lower than the limit, core dump files are limited to R limit F size bytes. That's kind of useful from a security perspective. If you don't want to do core dumps for security, then that's a good idea. R limit CPU. The R limit CPU limit specifies the max. Sorry, I'm on the wrong page here. Specifies the maximum number of seconds of CPU time in both system and user mode that can be used by the process. V3 requires that the SIG-X CPU signal be sent to the process when the soft limit is reached, but leaves other details unspecified. The default action for SIG-X CPU is to terminate the process with a core dump. It is possible to establish a handler for SIG-X CPU that does whatever processing is desired and then returns control to the main program. Therefore, on Linux, SIG-X CPU is sent once per second of consumed CPU time. If the process continues executing until hard CPU limit is reached, then the kernel sends a SIG-kill signal, which always terminates the process. Unix implementations vary in the details of how they deal with processes that continue consuming CPU time after handling a SIG-X CPU signal. Most continue to deliver SIG-X CPU at regular intervals. If aiming for portable use of the signal, we should code an application so that on first receipt of the signal, it does whatever cleanup is required and terminates. Alternatively, the program could change the resource limit after receiving the signal. R limit data. R limit data limit specifies the maximum size in bytes of a process's data segment. Some of the initialized, uninitialized data and heap segments described in section 6.3 attempts to break to extend the data segment. The program break beyond this limit fail with the error e-no-mem. As with R-limit as, the most common place where a program may hit this limit is in calls to functions in the malloc package. R-limit f-size. The R-limit f-size limit specifies the maximum size of files that the process may create in bytes. If a process attempts to extend a file beyond a soft limit, it is sent a SIG-XFSZ signal, and the system call write or truncate fails with the error EF-big. The default action for SIG-XFSZ is to terminate a process and produce a core dump. It is possible to instead catch this signal and return control to the main program. However, any further attempt to extend the file will yield the same signal and error. R-limit memlock. The R-limit memlock limit, BSD derived, absent from SUSV3, and available only on Linux and the BSDs, specifies the maximum number of bytes of virtual memory that a process may lock into physical memory to prevent the memory from being swapped out. This limit affects the mlock and mlock all system calls and the logging operation for memmap and shmctl system calls. We describe the details section 52. If the MCL future flag is specified when calling mlock all, then the R-limit memlock limit may also cause later calls to break to fail. R-limit message queue. The R-limit message queue limit. The R-limit message queue limit, Linux specific since 268, specifies the maximum number of bytes that can be allocated for POSIX message queue or the real user ID of the calling process. When a POSIX message queue is created using message queue open, bytes are deducted against this limit according to the following formula. In this formula, R-limit nice. I'm going to skip down to that. R-limit nice, Linux specific, specifies ceiling on the nice value that may be set for this process using sked, set scheduler, and nice. The ceiling is calculated as 20 minus R-limit cur, where R-limit cur is a set of R-limit nice soft resource limit. Refer to section 35.1 for further details. R-limit no file. The R-limit no... Is this just like a lot? Okay. The R-limit no file limit specifies a number one greater than the maximum file descriptor number that a process may allocate. Attempts, open pipe, socket, accept, so and so. Oh, these are cool. It lists all the open like syscalls. So you got open, pipe, socket. I thought connect was one, right? Maybe accept and socket. shm open, dupe2, fcntl, fdupe, and epoll create. To allocate descriptors beyond this limit fail. In most cases, the error is em file, but for dupe2, it is e bad file. And for fcntl with new file descriptors greater than or equal to the limit, it is e invalid. Changes to the rlimit no file limit are reflected in the value returned by sysconf sys open max. SysV3 permits but doesn't require an implementation to return different values for the call. How do I get all these ulimit values? Ulimit. Does this help? Help ulimit. So we say ulimit a. And then can I say dash S for soft? And then dash H for hard. Are those different at all? They look very similar to me. Oh yeah, the hard limit here for open files is way higher. Okay. Where do we leave off here? Oh, the SE open max thing. SysV3 permits but doesn't require an implementation to return different values for the call to sysconf SE open max before and after changing the rlimit no file limit. Other implementations may not behave the same as Linux on this point. SysV3 states that if the application set the soft or hard rlimit no file limit to a value less than or equal to the number of the highest file descriptor that the process currently has open, unexpected behavior may occur. On Linux, we can check the file descriptors a process currently has open by using readdir to scan the contents of the procpid.fd directory, which contains symbolic links for each of the file descriptors currently open by the process. The kernel imposes a ceiling on the value to which the rlimit no file limit may be raised. In kernels before 2625, the ceiling is hard-coded value defined by the kernel constant nropen, whose value is 1,000,000 roughly, 10 to the power of 20. A kernel rebuild is required to raise the ceiling. Since kernel 2625, the limit is defined as a value in the Linux specific procsys fs nropen file. Default value is in this file is 1,000,000. This can be modified by the superuser attempts to set the soft or hard rlimit no file limit rather higher than the ceiling value yield the error eperm. Okay. There's also system-wide limit on the total number of file descriptors. This is the one I've ran into most of the time. This thing is too low. Total number of files that may be opened by all processes. This limit is retrieved and modified via this Linux-specific procsys fs file max file. Let's see. So this guy, open files hard limit is about 500,000. And then if we cat out our procsys fs file max. That's a lot. This is why this is no longer an issue anymore on modern systems. I've ran into it in older systems before, but this number is huge. They're probably just like, let them open all the file descriptors they want. Only privileged cap system admin process can exceed the file max limit. In an unprivileged process, a system call that encounters the file max limit fails with the error en file. rlimit nproc. The rlimit nproc limit BSD derived absent from SysV3 and available only on Linux, and the BSD specifies the maximum number of processes that may be created for the real user ID. Or sorry, I wasn't reading. I was just my mind was wandering. So R limit N proc limit specifies a maximum number of processes that may be created for the real user ID of the calling processes. Okay, so this is what we were looking at before. Attempts to exceed this limit will fail with E again. The R limit N proc limit affects only the calling process. Other processes belonging to this user are not affected unless they are also set or inherit this limit. This limit is not enforced for privileged cap sysadmin or cap sysresource processes. Linux also imposes a system-wide limit on the number of processes that can be created on all users on Linux 2.4 and later. Linux-specific proc sys kernel threads max. Cat proc sys kernel threads max. That's not a lot. 1 million? That's not a lot. I mean, it's a lot considering you only have maybe what at most 128 cores on a typical machine. So you're definitely oversubscribing those cores, but threads are blocked doing I/O. There's a lot of things. I don't know. The C10K problem was 10,000, and that's only 2 orders of magnitude above that. So that isn't a lot. Okay, what is I reading here? To be precise, the R limit and proc resource limit and the threads max file are actually limits on the number of threads that can be created rather than the number of processes. The manner in which the default file for the R limit and proc resource limit is set has varied across kernel versions. In Linux 2.2, it was calculated according to a fixed formula. In Linux 2.4 and later, it is calculated using a formula based on the amount of available physical memory. Substitute doesn't specify the R limit and proc resource limit. The substitute mandated method for retrieving but not changing the maximum number of processes permitted to a user ID is via the call sysconf scchildmax. This sysconf call is supported on Linux, but in kernel versions before 2.6.2.3, the call does not return accurate information. It always returns the value 999 since Linux 2.6.2.3 with glibc 2.4 and later. This call correctly reports the limit by checking the value of R limit and proc resource limit. There is no portable way of discovering how many processes have already been created for a specific user ID. On Linux, we can try scanning all of the proc PID status files in the system and examine the information under the UID entry, which lists the 4 process user IDs in order, real effective save set and file system in order to estimate the number of processes currently owned by the user. Be aware, however, that by the time we have completed such a scan, this information may have already changed. R limit RSS, the R limit RSS limit, BSD derived absent from substitute 3 but is widely available, specifies the maximum number of pages that in a process's resident set. That is the total number of virtual memory pages currently in physical memory. This limit provided on Linux currently has no effect. Just going to ask AI here, describe what RSS in Linux is. So according to this book, it is the amount of virtual memory pages currently in physical memory. So you can have all these virtual memory pages that represent things like files on disks or swap memory, or even buffering, like buffered IO. And this is saying the virtual memory pages that correspond to physical memory. How much physical RAM is this process actually occupying right now? Virtual edge of space that hasn't been faulted in yet. Oh, it's good to know. Unique set size, I think, is what would be most helpful. Because a lot of that shared stuff, unless you're doing like big memory sharing things, like it's just a bunch of freaking libraries and stuff. Cool. That was very helpful. Thank you, AI. Where are we at? The limit is provided by Linux, but it counts not effect. Okay. In order, Linux 2.4 kernels up to including 2.4.2.9 RSS did have an effect on the behavior of madvs. MADV will need operation if this operation could not be performed as a result of encountering the RSS limits. Their EIO was returned to an error. R limit RATP priority, real time priority. Specifies a ceiling on the real time priority that may be set for this process using set schedule, and set param. Real time specifies the maximum amount of CPU time in microseconds that process running under a real time scheduling policy may consume without sleeping. This behavior, if this limit is reached, is the same as for R limit CPU. If the process reaches soft limit, then a sig x CPU signal is set to the process, and further sig x CPU signals are sent for each additional second CPU's time consumed. On reaching the hard limit, a sig kill signal is sent. Okay, that makes sense. Sig pending specifies a maximum number of signals that may be queued for the real user ID of a calling process. To exceed this limit, fail with error again. The R limit sig pending limit affects only the calling process. Other processes belonging to this user are not affected unless they are also set to inherit this limit. As initially implemented, the default value for our limit sig pending limit was 1024. Since kernel 2612, the default value has been changed to be the same value as the default value for our limit and proc. For the purpose of checking the R limit sig pending limit, count of queued signals includes both real-time and standard signals. Standard signals can be queued only once to a process. However, this limit is enforced only for sig_queue, even if the number of signals specified by this limit has already been queued to process belonging to this real user ID. It is still possible to use kill to queue one instance of each of the signals, including real-time signals. They are not already queued to a process. R limit stack. The R limit stack limit specifies the maximum size of process stack in bytes. attempts to grow the stack beyond this limit, result in the generation of a sig-v signal for the process. Since the stack is exhausted, the only way to catch this signal is by establishing an alternate signal stack as described in section 21.3. Since Linux 2.6.23, the R-limit stack limit also determines the amount of space available for holding process command line arguments and environment variables. See EXVE manual page for details. We're done, baby. Okay, summary. Processes consume various system resources. The get R usage system call allows a process to monitor certain other resources consumed by itself and by its children. The set R limit and set get limit system calls allow a process set and retrieve limits on its consumption of various resources. Each resource limit has two components: a soft limit, which is what the kernel enforces when checking a process resource consumption, and a hard limit, which acts as a ceiling on the value of the soft limit. An unprivileged process can set the soft limit for the resource up to any value in the range from 0 up to the hard limit, but can only lower the hard limit. A privileged process can make any change to either limit value as long as the soft limit is less than or equal to the hard limit. If a process encounters a soft limit, it is typically informed of the fact either by receiving a signal or via failure of a system call that attempts to exceed the limit. Write a program. Nope, not doing those. All right, 37 daemons. All right, it is 6:09. Let's record our progress here. So we are at 767, and it is 6:09. So 50 to 60, so that's 14 pages roughly in less than an hour. Seems to be what I'm running at. Okay. Okay. Let's chat about daemons a little bit up front. So, my definition of a daemon is something that like runs under a process manager like systemd or well, mainly systemd these days, but any type of process manager. That's what I would refer to as a daemon these days. But back in the day, there was like this concept of like daemonizing a process. You're certainly not running under a terminal, a TTY. You might be running under a shell, but you're not running under a running under a terminal, a TTY, and you're not running under a I guess I would say that you're not running under a terminal if you're a daemon. So anything that you spawn off from your shell session inside of a terminal, like none of that stuff is like daemon stuff. So I guess one question I do have for the AI, but I kind of don't want to ask it up front, is like what does daemonizing mean? Because there used to be like functions that you could call to like daemonize a process. I've seen that like several times over my career, and I just assumed it's like, okay, this thing runs in the background, it's not part of a shell, it's not part of a terminal session, I should say, and it's being managed by some type of process manager. That's always what I assumed. So I want to come back to like how daemonizing as a concept was implemented and if it's still valid in like modern systemd systems. This chapter examines the characteristics of daemon processes and looks at the steps required to turn a process into a daemon. We also look at how a log message from a daemon, how to log messages from a daemon using the syslog facility. Overview. A daemon is a process who has the following characteristics. It is long-lived. Often a daemon is created at system startup and runs until the system is shut down. It runs in the background and has no controlling terminal. Exactly. The lack of controlling terminal ensures that the kernel never automatically generates any job control or terminal-related signals for a daemon. Exactly. So I was right. That's exactly what I said. Daemons are written to carry out specific tasks, as illustrated by the following examples. Cron, a daemon that schedules commands on a scheduled time. SSHD, the secure shell daemon, which permits logins from remote hosts using a secure communications protocol. HTTPD, the HTTP server daemon Apache, which serves web pages. INetD, the Internet Super Server daemon described in section 65. Wow, I didn't know we were going to get into INetD. This is like the busted old freaking accepts everything on the internet daemon, which listens for incoming network connections on specified TCP ports and launches appropriate server programs to handle these connections. It's so jank. Many standard daemons run as privileged processes, effective user ID of 0. Really? I guess if they need to do privileged things, and they'll run as privileged process, like SHD probably, and thus should be coded following the guidelines provided in chapter 38. What is in 38? 38 is writing secure privileged programs. Okay, I guess that's appropriate after the daemon section. It is a convention not usually observed that daemons have names ending with the letter D. On Linux, certain daemons are run as kernel threads. A kernel thread is like kernel code. The code of such daemons is part of the kernel, and they are typically created during system startup. When listed using PS, the names of these daemons are surrounded by square brackets. Is that what that is? I never knew that. PS aux. Less. There's like K-thread stuff. Yeah, all this stuff. K-worker. I mean, obviously it's like a kernel worker, but... Okay. Init splash. Making a splash. I mean, I just always assumed this is all kernel. I guess it is kernel stuff, but like I didn't consider it as like a separate daemon, but I guess it is, right? It's kernel code that is running in kernel. Does it run in kernel space? Do kernel daemons in Linux run in the kernel space or user space? I think it's user space, right? True kernel daemons, kernel space. Historically and conceptually, a kernel daemon is a thread that runs entirely in kernel space. No user virtual address space, no user mode execution scheduled like a task, but always in kernel mode. Oh, so it's just like what they call the kernel schedulable thing. What do they call it? KS something? Unit? KSU? Is that what it is? Let me go back to the index here and look that up. I think it's KSU. KSE, kernel scheduling entity. I thought it was an E. Okay. Scheduled like a task, but always in kernel mode. These are implemented as kernel threads, K-threads. You'll see them in PS output, but that's just a scheduler exposing them, not because they're user processes. Key properties created with K-thread create, K-thread run, task struct exists. Daemons that do kernel work, user space. Yeah, these are just totally normal user space programs. Okay. can you explain the relationship between KSE's kernel schedulable entities and tasks inside the kernel? Yeah, this is what I've been familiar with before, is the task struct. And Linux schedules task struct. There is exactly one fundamental schedulable object. Every runnable thing, whether you think of it as a process thread or kernel thread, is represented as a task struct. What term KSE comes from is conceptual OS theory term, not a Linux API term historically. So and so. Linux explicitly rejected this model. Everything is a task. That's what I've been familiar with in the past, is everything is a task. Before reading this book, and they came up with this terminology KSE, like. Okay, cool. Where did we leave off? Creating a daemon? Was that? No, we were in this square brackets PD flush, which periodically flushes dirty pages to disk. What's funny is, like, wasn't like the whole argument back in the 90s or whatever, like microkernel versus monolithic? Doesn't this mean that like Linux is a microkernel? Let's ask AI, see what it says. I doubt it would say yes. Let's go back to the kernels. Yeah, this thing. Since Linux has all of these kernel daemons running, wouldn't that make wanting to perform kernel functionality, wouldn't that kind of make the Linux kernel a micro kernel of sorts versus the label it normally gets of being monolithic? It's still monolithic, but it borrows some structural tricks that look microkernel-ish from the outside. I mean, that's what I would say myself. That's a reasonable take. I was hoping it would give me a hotter take than that, though. What monolithic versus micro actually means is not about how many threads exist, but whether the things are daemon-like. Well, I mean, it has kernel daemons. It's about where privileged functions execute and how components interact. Okay. Monolithic kernel. Most OS services run in kernel space. Communication via direct function calls share the same address space. Failure, the whole kernel can go down. Examples: Linux, BSD, traditional Unix, Windows. Microkernel. Kernel does as little as possible: scheduling, IPC, address spaces, file system, networking, drivers run in user space, communication via message passing, failures are isolated, mock, Minix, SEL4. Mock is the only one that I have any experience with, and I don't even know if that's like, I guess GNU Herd is like another one, right? But I don't think mock is like still considered microkernel now that Apple's kind of like had its way with it. What Linux kernel threads actually are. Daemons. Is the mock kernel the one used for Mac OS? And if so, is it still considered a micro kernel? macOS uses mock, but the system as a whole is not a microkernel OS. The kernel XNU is best described as a hybrid kernel. Yeah, that's what I remember reading. So they just like bolted like BSD onto the mock kernel, I guess. I don't know. I don't know what they did, to be honest. Don't care anymore. Creating a daemon. To become a daemon, a programmer performs the following steps. Perform a fork, after which the parent exits and the child continues. As a consequence, the daemon becomes a child of the init process. This step is done for two reasons. Assuming the daemon was started from the command line, the parent's termination is not noticed by the shell, which then displays another shell prompt and leaves the child to continue in the background. Child process is guaranteed to be a process group leader, since it inherited its process group ID from the parent and obtained its own unique process ID, which differs from the inherited process group ID. This is required in order to be able to successfully perform the next step. Child process called set SID to start a new session and free itself of any association with the controlling terminal. If the daemon never opens any terminal devices thereafter, then we don't need to worry about the daemon reacquiring a controlling terminal. If the daemon might later open a terminal device, then we must take steps to ensure that the device does not become the controlling terminal. We can do this in two ways. Specify the no CTTY flag on the open that may apply to a terminal device. Alternatively, more simply, perform a second fork after the set SID call again. And again, have the parent exit and the grandchild continue. This ensures that the child is not the session leader, and thus, according to SysMV conventions for the acquisition of a controlling terminal, which Linux follows, the process can never reacquire a controlling terminal. On implementations following the BSD conventions, a process can obtain a controlling terminal only through an explicit ioctl TIOSC TTY operation. And so the second fork has no effect with regard to the acquisition of the controlling terminal, but the superfluous fork does no harm. Clear the process umask to ensure that when the daemon creates files and directories, they have the requisite permissions. Change the process current working directory, typically to the root directory. This is necessary because the daemon usually runs until the system is shut down. If the daemon's current working directory is on a file system other than the one containing slash, then that file system can't be unmounted. Alternatively, the daemon can change its working directory to a location where it does its job, or a location defined in its configuration file, as long as we know that the file system containing this directory never needs to be unmounted. For example, cron places itself in var spool cron. Close all open file descriptors that the daemon has inherited from the parent. A daemon may need to keep certain inherited file descriptors open, so this step is optional or open to variation. This is done for a variety of reasons. Since the daemon has lost its controlling terminal and is running in the background, it makes no sense for the daemon to keep file descriptors 0, 1, 2 open if these refer to the terminal. Furthermore, we can't unmount any file system on which the long-lived daemon holds files open. And as usual, we should close unused open file descriptors because the file descriptors are a finite resource. Some Unix implementations, e.g. Solaris 9, and some of the recent BSD releases provide a function named close from n, or similar, which closes all descriptors greater than or equal to n. This function isn't available in Linux. After having closed file descriptors 0, 1, 2, a daemon normally opens dev null and uses dup2 or similar to make all those descriptors refer to this device. This is done for two reasons: to ensure that if the daemon calls library functions to perform I/O on these descriptors, those functions won't unexpectedly fail. It prevents the possibility that the daemon later opens a file descriptor 1 or 2, which is then written to and thus corrupted by a library function that expects to treat these descriptors as standard output and standard error. Dev null is a virtual device that always discards data written to it. When we want to eliminate the standard output or error of a shell command, we can redirect it to this file. Reads from this device always return end of file. We now show the implementation of a function become daemon that performs the steps described above in order to turn the caller into a daemon. Become daemon flags. Become daemon function takes a bit mask argument flags that allows the caller to selectively inhibit some steps as described in the comments in the header file in listings 37.1. That's the other thing. Like all these like daemonize, become daemon stuff, it's never like built into a standard library. It's always like some like random thing implemented somewhere. All right. Ooh, it's just me, myself, and I. All right. The implementation of become daemon function is in 37.2. The GNU-C library provides a non-standard function, daemon. Okay, there is a glibc version that turns the caller into daemon. The glibc daemon function doesn't have an equivalent of the flags argument of our become daemon function. I still would rather use that because it's like distributed. This is just like some code in a book. So these are just a bunch of flags. Okay. So it does its fork, -1, then we just return -1. If it was 0, then we break out of the switch. If it's default, then we exit success. So default would be the parent. Case 0 would be the child. So the parent terminates. And then the child says, hey, I'm going to set my SID, my session ID, to -1. Or no, I'm going to set my session ID, which makes it become a leader of new session. And then I'm going to do my fork again to make sure that the child is not a leader. So this leader now is dead. So now the grandchild goes through and does these things conditionally, setting the UMass, it shadur, Yeah, making sure the file descriptors are closed, and then closing standard in, and then opening up dev null. Why don't they close standard out and standard error? No. Okay, oh, because these dupe calls automatically close them. So it closes the file node, creates a file descriptor, and then does a dupe of standard in file node to standard out. Huh? Why don't you write this file descriptor to standard in file node? Oh, this just asserts that it is. Okay. I would assume that he would write to it, but he just says, make sure that it's asserted that it's the thing, because I've closed everything up here. Okay. It's a bit weird, but okay. If we write a program that makes, oops, on the wrong page here. If we write a program that makes a call to become daemon and then sleeps for a while, we can use PS to look at some of the attributes of the resulting process. So we do our test become daemon, then we PS-C, and our parent is now the init. We don't show some source code for daemons, test become daemon, since it's trivial, but the program is provided in the source code distribution of the book. We have new session ID, no controlling terminal. The output of PS, the question mark under the TT heading indicates that the process has no controlling terminal. From the fact that the process ID is not the same as the session ID, we see that the process is not the leader of the session, and so won't require a controlling terminal if it opens a terminal device. This is as things should be for a daemon. Guidelines for writing daemons. As previously noted, a daemon typically terminates only when the system shuts down. Many standard daemons are stopped by application-specific scripts executed during system shutdown. Those daemons that are not terminated in this fashion will receive a sigterm signal, which the init process sends to all of its children during system shutdown. By default, sigterm terminates a process. Daemon needs to perform any cleanup before terminating. It should do so by establishing a handler for the signal. This handler must be designed to perform such cleanup quickly, since your init follows up the sigterm signal with a sigkill signal after 5 seconds. This doesn't mean that the daemon can perform 5 seconds worth of CPU work. Init signals all the processes on the system at the same time, and they may all be attempting to clean up within that 5 seconds. Since daemons are long-lived, we must be particularly wary of possible memory leaks and file descriptor leaks, where an application fails to close all of the file descriptors it opens. If such bugs affect the daemon, the only remedy is to kill it and restart it, fixing the bug. Many daemons need to ensure that just one instance of the daemon is active at one time. For example, it makes no sense to have 2 copies of the cron daemon both trying to execute scheduled jobs. In section 55.6, we look at technique for achieving this. Cool. Look forward to that. Using sighup to reinitialize a daemon. Yep. The fact that many daemons should run continuously presents a couple of programming hurdles. Typically, a daemon reads operational parameters from associated configuration file at startup. Sometimes it is desirable to be able to change these parameters on the fly without needing to stop and restart the daemon. Some daemons produce log files. If the daemons never close the log file, then it may grow endlessly, eventually clogging the file system. In section 18.3, we noted that even if we remove the last name of a file, the file continues to exist as long as any process has it open. What we need is a way to telling the daemon to close its log file and open a new file so that we can rotate log files as required. The solution to both of these problems is to have the daemon establish a handler for SIG-HUP and perform the required steps upon receipt of the signal. In section 34.3, we noted that SIG-HUP is generated for the controlling process on disconnection of the controlling terminal. Since the daemon has no controlling terminal, the kernel never generates a signal for the daemon. Therefore, daemons can use SIG-HUP for the purpose described here. The log rotate program can be used to automate rotation of daemon log files. See the log rotate manual page for details. Listing 37.3. One thing I want to check here is how do you test if you have controlling terminal in Linux? I think you just like do like read link dev tty. I think it's dev tty, right? Dev grep tty. I mean, there's a bunch of tty's here, right? Oh, it's not read link, because that is not a soft link. As the kernel, so you just say, hey, is my standard in a tty? No, because you could have no. Yeah. It's just FD refers to as a TT. Do you have a controlling terminal? Yeah, this is it. Man tc get process group. Get and set terminal foreground process group. And it gives you a PID. No. No. Yeah, this one here. What is T? Help test. What is -T? True if FD is open on a terminal. E, file exists. I guess you could, yeah, just say, does this thing exist? Can you not have a process that was spawned from a shell but doesn't have its FD 0 or 1 or 2 set to a TTY, but still be part of a process group and session that has a controlling TTY? I think you got to use this OpenDev TTY. And if that is part of a daemon, then it'll okay. So we're talking about SIGHUP here. The log rotate program can be used to automate rotation of daemon log files. See the log rotate. This is all handled by journald now. Listing 37.3 provides an example of how a daemon can employ SIGHUP. This program establishes a handler for SIGHUP, becomes a daemon, opens a log file, and reads its configuration file. SIGHUP handler sets a global flag variable HUP received, which is checked by the main program. The main program sits in a loop, printing a message to the log file every 15 seconds. Call sleep. Okay. Let me reread this. Example program how a daemon can employ SIGHUP. This program establishes handler for SIGHUP, becomes a daemon, opens a log file, and reads its configuration file. The SIGHUP handler just sets a global flag variable HUP received, which is checked by the main program. The main program sits in a loop, printing a message every to a log file at 15 seconds, and calls sleep. And this loop are intended to simulate some sort of processing being performed by a real application. After each return from sleep in this loop, the program checks to see whether HUP receive has been set. If so, it reopens the log file, rereads the configuration file, and clears the HUP receive flag. For brevity, the functions log open, log close, log message, and read config file are omitted from the listing 37.3, but are provided with the source code distribution of this book. The first three functions do what would expect in their names. The reconfig file simply reads the file, configuration file, and echoes it to the log file. Some daemons use alternative methods to reinitialize themselves on receipt of SIGHUP. They close all their files and then restart themselves with exec. The following is an example of what we might see when running a program in listing 37.3. We begin by creating a dummy configuration file and then launching the daemon. So echo start into some config file. We say daemon SIGHUP, and then we cat out its log. It has open the log file, read the config file start. Now we modify the configuration file and rename the log file before sending SIGHUP to the daemon. We echo changed, we override it, and then we run date. We move the log to the old, and then we kill all HUP daemon SIGHUP. Then we ls the log. Now we got a new one. And we count the old one. It said, hey, I'm closing my stuff now. The output of ls shows that we have both an old and new log file. When we use cat to view the contents of the old log file, we see that even after mv command was used to rename the file, the daemon continued to log messages there. At this point, we could delete the old log file if we no longer need it. When we look at a new log file, we see that the configuration file has been reread. Yep, and it's changed. Note the daemon log and configuration files are typically placed in standard directories, not in temp directory as done in the program. By convention, configuration files are placed in etc or in one of the subdirectories, while log files placed in var log. Daemon programs commonly provide command line options to specify alternate locations instead of the defaults. Logging messages and errors using syslog. This really isn't necessary anymore. With journal D, I'd rather learn about journal D than syslog. There's a lot about syslog. Okay, we'll speed read it. I'm just gonna speed read the shit out of this thing. Okay. Because I mean, this is all kind of like so out of date now with journal CTL and journal D. Logging messages in errors using syslog. When writing a daemon, one problem we encounter is how to display error messages. Since the daemon runs in the background, we can't display messages on the associated terminal as we would typically do with other programs. One possible alternative is to write message application-specific log file, as is done in the program listing 37.3. The main problem with this approach is that it's difficult for a system administrator to manage multiple application log files and monitor them all for error messages. Syslog facility was devised to address this problem. Overview: Syslog facility provides a single centralized logging facility that can be used to log messages by all applications on the system. An overview of this facility is provided in figure 37.1. So you have the kernel, user process on remote host. Kernel, user process on remote host. The kernel hits print K, syslog to proc K message. I've used that before. Klog D, syslog. User process called syslog3. There's a devlog, Unix domain datagram socket. Okay, so all this goes to Unix domain datagram socket devlog. I don't know where this comes into play here. Process on the remote host, TCP IP network, UDP port 514, internet domain datagram socket, all going into syslog D, configuration file, and then syslog D is configured to do whatever it wants. Terminal console, FIFO, disk file, remote host, logged in user. Okay, this is all out of date with journal D. Okay, the syslog facility has two principal components: the syslog daemon and the syslog3 library function. The system log daemon, syslog D, accepts log messages from two different sources: a Unix domain socket devlog, which holds locally produced messages, and if enabled, the internet domain socket UDP port 514, which holds messages sent across the TCP network. On some other Unix implementations, syslog socket is located var run log. Each message preceded by syslog has a number of attributes, including a facility which specifies a type of program generating the message and a level which specifies the severity priority of the message. Syslog D daemon examines the facility and level of each message and then passes it along to any of several possible destinations according to the dictates of the associated configuration file. Under etc syslog conf, I definitely don't have that. Cat etc syslog. Nope. Possible destinations include terminal or virtual console, a disk file, FIFO, disk file, a FIFO, one or more or all logged in users, or a process, typically another syslog D daemon, on another system connected via TCP IP network. Sending the message to a process is another system. Sending the message to a process on another system is useful for reducing administrative overhead by consolidating messages from multiple systems in a single location. A single message may be sent from to multiple destinations or none at all. A message is sent with different combinations of facility and level can be targeted at different destinations or to different instances of destinations, i.e. different consoles, different disk files, and so on. Sending syslog messages to another system via a TCP network can also help when detecting system break-ins. Break-ins often leave traces in the system log, but attackers usually try to cover up their activities by erasing log records. With remote logging, an attacker would need to break into another system in order to do that. The syslog3 library function can be used by any process to log a message. This function, which we describe in detail in a moment, uses its supplied arguments to construct a message in a standard format that is placed on the devlog socket for reading by syslog D. It's a Unix domain socket. An alternative source of this message placed on devlog is the kernel log daemon klog D, which collects kernel log messages produced by the kernel using its print K function. These messages are collected using either of two equivalent Linux specific interfaces, the proc K message file and the syslog2 system call, and then placed on devlog using syslog3 library function. Although syslog2 and syslog3 share the same name, they perform quite different tasks. An interface syslog2 is provided with glibc under the name. Wait a minute. That's a man to syslog, or syslog klog ctl, read and or clear kernel messages. If we do man sys calls, syslog, log, log. Okay. Klog ctl, okay. Nope, you're looking for C library function syslog, which talks to syslog D, C syslog 3 for details. This page describes the kernel syslog system call, which is used to control the kernel's print K buffer. The glibc wrapper function for the system call is called klog ctl. So you can close, open. The thing I like about looking at the syscall table when I'm reading through this stuff is like it's more conserved over iterations and changes to the Linux ecosystem. Like they preserve these interfaces longer than things that are library functions. Like this whole syslog D thing, like if I psaux grep for syslog, it ain't here. But if I look for journal, there it is. Okay. Where did I leave off? Oh, here we go. The syslog facility originally appeared in 4.2 BSE, but is now provided on most Unix implementations. Syslog 3 has standardized syslog 3 and related functions, but leaves the implementation and operation of syslog, as well as the format of the syslog conf file unspecified. The Linux implementation of syslog D differs from the man 3 syslog. Over here. Yeah? Original BC facility permitting some extensions to the message processing rules that can be specified in syslog-conf. Syslog API. The Syslog API consists of 3 main functions. The openlog function establishes default settings that apply to subsequent calls to syslog. The use of openlog is optional. If it is omitted, a connection to the logging facility is established with default settings on the first call to syslog. So it looks like the library function and the syscall itself for syslog are conserved. They just pointed the journal D now instead of syslog D. The syslog function logs a message. The close log function is called when we have finished logging messages to disestablish the connection with the log. None of these functions returns a status value. In part, this is because system logging should always be available. The system administrator is soon likely to notice if it is not. Furthermore, if an error occurs with system logging, there is typical little that an application can usefully do to report it. The GNU C library also supports a function voids v-syslog in priority constchar format va _ list args. This function performs the same task as syslog but takes an argument list previously processed by the standard argument 3 API. Thus, v-syslog is to syslog what vprintf is to printf. Syslog 3 doesn't specify v-syslog and it's not available in all Unix implementations. Establishing a connection to the system log. The openlog function optionally establishes a connection to the system log facility and sets that defaults that apply to subsequent syslog calls. The ident argument is a pointer to a string that is included in each message written by syslog. Typically, the program name is specified for this argument. Note that openlog merely copies the value of this pointer. As long as it continues to call syslog, the application should ensure that the reference to the string is not later changed. The ident is specified as null. Then, like some other implementations, the glibc syslog implementation automatically uses the program name as the ident value. However, this feature is not required by sus v3 and is not provided on some implementations. Portable applications should avoid relying on it. The log options argument in openlog is a bitmask created by ORing together any of the following constants. Log cons, if there is an error sending to the system logger, then write the message to the system console dev console. What is the system console? What is dev console? It's a serial port. If I cat out my dev console to word count -l sudo bang bang, did I get that right? No. Come on. It's a character device. It's not a block device. So a character device is just, you're just gonna be able to read off of it indefinitely. So you can't cat it. If I cat dev console here, sudo bang bang, it's just gonna be nothing. Sudo -i echo test into dev console, and if I do control F1, I guess I'm already here, right? Yeah, okay. Cat proc consoles tty0. Wonder if it's in a different login terminal. I'm gonna attempt this. It might break my Wayland session though. Control Alt F2 maybe. Nope. F3. Nope. F4. Oh. That's TTY4, 3, 2, 1. 6, 5, 4, 7, 6. I think I might have killed my excellence. No, I got it back. I got it back. Yay. Sorry, I thought I killed my Wayland session there. Sometimes when you switch those, it goes a little haywire. Okay, so it went to TTY0, but because that's not wired up to anything here, it didn't get printed out. Okay, I don't really care. Let's continue on reading. Get through the rest of this. Get to bed. Oh, this is lots of syslog stuff. Okay. Log and delay. Open the connection to the logging system, i.e. the underlying Unix domain socket devlog immediately. By default, log node o delay. The connection is opened only when and if the first message is logged with syslog. The end delay flag is useful in programs that need to precisely control when the file descriptor is allocated. One example of such requirement is a program that calls to root. After to root call, the devlog path name will no longer be visible, and so an open log call specifying an end delay must be performed before the to root. The TFTPD trivial file transfer daemon is a example program that uses end delay for this purpose. Log no wait. Don't wait for any child process that may have been created in order to log the message. On implementations that create a child process for logging messages, log no wait is needed if the caller is also creating and waiting for children, so that syslog doesn't attempt to wait for a child that has already reaped by the caller. On Linux, log no wait has no effect since no child processes are created when logging a message. I was gonna say, like, creating child processes when waiting for a message is like, for a logger, is like pretty heavyweight. Log O delay. This flag is the converse of no delay or end delay. Connecting to the logging system is delayed until the first message is logged. Is the default and not need to be specified. Log P error. Write messages to standard error as well as the system log. Typically, daemon processes close standard error or redirect it to dev null, in which case log P error is not useful. Log the calling process ID. Log the caller's process ID with each message. Employing log PID in a server that forks multiple children allows us to distinguish which process logged a particular message. Okay. All of the above constants are specified in Subspace 3 except for log P error, which appears on many but not all other Unix implementations. The facility argument to OpenLog specifies the default facility value to be used in subsequent calls to syslog. Possible values for this argument are listed in table 37.1. The majority of the facility values in table 37.1 appear in Subspace 3 as indicated by the Subspace 3 column of the table. Exceptions are log auth privileged and log FTP, which appear only on a few Unix implementations, and log syslog, which appears on most implementations. The log auth privilege value is useful for logging messages containing passwords. Oh, no. Never do that. Or sensitive information to a different location than log auth. The log current facility use value is used for kernel messages. Log messages for this facility can't be generated from user space programs. The log current constant has the value 0. If it is used in a syslog call, the 0 translates to use the default level. Log current facility value is used for kernel messages. Log message for this facility can't be generated from user space programs. The log current constants has a value 0. If it is used in syslog call, the 0 translates to use the default level. Okay, that makes sense. Okay, what is this private security and authorization message? Why would you want to, even then, it's like, no, don't put passwords there. Okay, it was just like facilities. To write a log message, the priority argument is created by orienting the facility value and the level value. Facility indicates the general category of the application logging the message and is specified as one of the values listed in table 37.1. If omitted, the facility defaults to the value specified in a previous OpenLog call or to the log user if the call was omitted. The level value indicates the severity of the message and is specified as one of the values in table 37.2. All of the level values listed in this table appear in Subspace 3. Level values: debug info, notice, warning, error, crit, alert, emergency. So these you normally see in like leveled loggers. The remaining arguments to syslog are a format string and corresponding arguments in the manner of printf. One difference from printf is that the format string doesn't need to include a terminating new line character. Also, the format string may include the 2-character sequence %m, which is replaced by the error string corresponding to the current value of error no, i.e. the equivalent of stir error no. The following code demonstrates the use of openlog and syslog. So you openlog with a bunch of stuff. You say, hey, bad argument, log error. Yeah, okay, great. Since no facility is specified in the first syslog call, the default specified by openlog is used. In the second log call, explicitly specifying log user overrides the default established by openlog. From the shell, we can use the logger command and add entries to the system log. The command allows specification of the level and ident tag to be associated with the log message. For further detail, see the logger manual page. The logger command is weakly specified in Subspeed 3, and a version of this command is provided by most Unix implementations. I gotta block the spammer. Boop. Okay, it is an error to use syslog to write some user-supplied string in the following manner. Syslog prior to user-supplied string. The problem with this code is that it leaves the application open to so-called formatting attacks. If the user-supplied string contains format specifiers, e.g. %s, then results are unpredictable and, from a security point of view, potentially dangerous. The same observation applies to the use of conventional printf functions. We should instead rewrite all the calls above as follows. Okay, that makes sense. Closing the log, when we have finished logging, we can call close log to deallocate the file descriptor used for the devlog socket. Since a daemon typically keeps a connection open to the system log continuously, it is common to omit calling close log. Filtering log messages, the set log mask function sets a mask that filters messages written by syslog. Okay, doke, artichoke. 2 more pages. Almost done here. Set log mask. Any message whose level is not included in the current mask setting is discarded. The default mask value allows for severity levels to be logged. All severity levels to be logged. The macro log mask defined in syslog h converts the level values in table 37.2 to bit values suitable for passing to set log mask. For example, to discard all messages except those with priorities of log error and above, we would make the following call. The log mask macro is specified by Subspeed 3. Most Unix implementations, including Linux, also provide the unspecified macro log up to, which creates a bit mask filtering all messages at a certain level and above. Using this macro, we can simplify the previous set log mask called the following. The etc syslog conf file, this etc syslog conf configuration file, controls the operation of syslog d daemon, which no longer exists. This file consists of rules and comments starting with the hash character. Rules have the following general form: facility.level action. Together, the facility and level are referred to as the selector since they select the messages which the rule applies. These fields are strings corresponding to the values listed in table 37.1 and table 37.2. The action specifies where to send the message matching the selector. Whitespace separates the selector and the action parts of a rule. The following are examples of rules. You got a star error, so that says like, hey, any facility that has level error, set to dev tty10, auth notice root. Don't know what that means. Maybe email to root. And then we have mail none, news none, star debug goes to var log messages, but it says minus. Which usually it means like ignore the error if it doesn't exist. The first rule says that messages from all facilities with the level of error or higher, so it is or higher, should be sent to the dev tty console device. The second rule says that authorization facility auth-log messages with a level of notice or higher should be sent to any consoles or terminals where root is logged in. This particular rule should allow a logged in root user to immediately see messages about failed SU attempts, for example. The last rule demonstrates several of the more advanced features of rule syntax A rule can contain multiple selectors separated by semicolons. The first selector specifies all messages using the wildcard for facility and debug for the level, meaning all messages of the level debug, the lowest level and higher. So then why would you need mail none and news none? On Linux, as on some other Unix implementation, it's possible to specify level as star with the same meaning as debug. However, this feature is not available in all syslog implementations. Normally, a rule that contains multiple selector matches messages corresponding to any of the selectors, but specifying a level of none has the effect of excluding all messages belonging to that corresponding facility. Thus, this rule sends all messages except for mail and news facilities to the file var log messages. The hyphen preceding the name of the file specifies that a sync to the disk does not occur on each write up to the file. This means that writes are faster, but some data may be lost if the system crashes after the write. Whenever we change a syslog.conf file, we must ask the daemon to reinitialize itself from this file in the usual fashion: kill all hup syslog-d. Further features of the syslog.conf rule syntax allow for much more powerful rules than we have shown. Full details are provided in the syslog.conf manual page. Don't care. Summary. A daemon is a long-lived process that has no controlling terminal, i.e. it runs in the background. Daemons perform specific tasks such as providing a network login facility or serving web pages. To become a daemon, a program performs a standard sequence of steps, including calls to fork and set SID. Where appropriate, daemons should correctly handle the arrival of the sigterm and sighub signals. The sigterm signal should result in the orderly shutdown of the daemon, while a sighub signal provides a way to trigger the daemon to reinitialize itself by rereading its configuration file and reopening any log files it may be using. The syslog facility provides a convenient way for daemons and other applications to log error and other messages to a central location. These messages are processed by the syslog-d daemon, which redistributes the messages according to the dictates of the syslog.conf configuration file. Messages may be redistributed to a number of targets, including terminals, disk files, logged-in users, and via a TCP/IP network to other processes on remote hosts, typically other syslog-d daemons. Further information. Perhaps the best source of further information about writing daemons is the source code of various existing daemons. That is a great point right there. Just start reading good open source software. I plan on doing some of that soon on stream. Exercise, write a program. Nope, not doing that. Don't care about logging. 38, we made it. All right, I am logging off for the night. 7:15, I'm ready to get to bed. All right, we did it. Let me do my log here. So we are at 783, and it is 7:15. So far, we've had 3 days now of 100 pages each day. And, I mean, I'm going fast, but it's not so fast that I feel like I'm, just not absorbing stuff that's really important. There are some things that I've skipped over that are just I can tell this is not super important. But even something like syslog, I actually read all that. But there was some stuff in the job control section. I'm just the signal stuff around job control. I just don't care. I just don't care. Job control is a shell functionality. Most of the software I write is daemons. It's not stuff that's running under a terminal. There's session ID doesn't matter. The freaking process group ID doesn't matter. None of that stuff matters. So, anyways, all right. So we are at 38. So writing secure privileged programs. So let's just take a quick look at what we have on deck for tomorrow. So we're going to 882 or 883, we'll say, because we're at 783. So we're going to 883, which will be all the way down to here. I would say 887 right here. So that's 43. So yeah, writing secure privilege programs. Definitely interested in doing some of that. Capabilities, sure. You know, I've have a good amount of experience with capabilities already, but it's always useful to learn more. Login accounting. Not super excited about this, but it's good to know. Fundamentals of shared libraries, definitely excited about that one. Advanced features of shared libraries, definitely excited about that one. Inter-process communication overview. And that would be the start of IPC. So we got a lot of really fun stuff tomorrow. I'll be getting started early since it is Saturday tomorrow and I don't have training in the morning. Yeah, I'm excited. That's 300 pages in 3 days. And I'm excited for tomorrow. I'll have this book done ideally by Thursday next week. Cool. Well, I'm going to go ahead and end the stream there. I'll be on tomorrow morning, ideally as early as possible to get this stuff done. All right.